Okay, welcome. Hope you had a good summer. I'm Jason Bakos. This is CSCE 611, Advanced Digital Design. As you probably know, we have two sections. Both sections meet here on Monday for lecture, and then one of the sections is on lab on Wednesday, and the other one's in lab on Friday, same time. The lab is, hold on. The lab is, lab's in this building, room 3D22, the upstairs Linux lab, third floor Linux lab. D, yeah, 3D22, right, yeah. So in this course, I'm using the CSCE Dropbox, also known as the Moodle website. That's dropbox.csc.sc.edu. This will be last year we get to use that. If the university is going to force us to switch to Blackboard. I have my lectures are recorded and they're all put on my YouTube channel there in case you miss a lecture, you want to hear something again, or if you want to see what's in the future. We're going to be using software and hardware that's in 3D22. And so there's some parts of the course of the lab work you can do at home, but you have to be in the lab to use the FPGA boards that we have in there. Okay. Make sure that you're receiving email at email.sc.edu for important announcements. And we'll be working, the labs will be done in teams of 2. And so you'll have to pick a lab mate and coordinate with your lab mate on how you want to collaborate, how you want to share files. If you have any issues with the lab, you can contact Ryan Austin for any support in the lab or on the Moodle website. So if you can't log in to the website, dropbox.csc.sc.edu. We have a textbook. It's Digital Design and Computer Architecture by Harris and Harris. And if you go to the second page there, it shows actually 2 covers, because I didn't realize until a couple weeks ago that apparently there is a version of the textbook for the RISC-V processor, which is actually more appropriate because we're going to be doing RISC-V in this course, as opposed to the MIPS architecture that you all learned about in 212. So either textbook is fine. If you've got the first one, which is the one that I set up in the bookstore, that one's fine too. Because MIPS and RISC-V are very similar. Okay, so I've got section 5 is the ABET learning outcomes. Section 6 are important dates. I think I've got them all there. We have a cancellation on September 2nd, right, which is next Monday, which really stinks because that's be our second lecture. But I'll be lecturing in lab this week. And then October 14th through 18th, I have the whole week canceled, including the lecture on Monday for fall break, because I'm traveling that Monday, even though technically fall break is, I think, just Thursday and Friday, but I'll be traveling on that Monday. And then, of course, as usual, after Thanksgiving, we just have a week left of the semester after that. Okay, I've got 2, if you go to the next page there, section 7, I have 2 TAs. They're both my PhD students, Soyash Singh and Angela Kalinko. You'll meet them, I'll introduce you to them on Wednesday in lab, or Friday, if you have the Friday lab. And the section 8 has the grading structure. The course has 4 labs that are group-based, so all members of the group get the same score on those labs. They're applied labs projects. And then we also have a lot of individual scores as well. We have quizzes and midterm and final exam. And if you add up all the weights, the grade weights, it adds up to 117.5%, which is done deliberately so you can drop an exam or a lab, right? So that way you can kind of customize the course a little bit. Some students enjoy working on the projects more, and they don't like studying for the exams as much. Other students might get stuck with a bad lab partner, or they get behind in the labs. The labs build on one another too, so it's possible to get behind. And so in that case, you can drop the last lab and rely more on your exam scores, exam and quizzes. Section 9 is the schedule, which we should be sticking with pretty closely, because this course is pretty stable. Haven't changed it much over the last few years. Let's see, Section 9 is about disability support. If you need help with that, you have to go through the disability office. Section 11 says we may need to change the syllabus, although we generally don't. That's if we have some kind of university closure or something and we have to drop a lab or something. Section 12 is grading scale standard. Section 13 is the academic honesty policy, which is a little tricky in this class because we're going to be using CAD tools, and CAD tools are awful, all of them. They're hard to use and not very user-friendly, and they crash a lot. And so working in the lab gives you an opportunity to get help with the CAD tools from other students in the lab, which is great. If you're having a problem with a crash or you're trying to do something and you're having trouble figuring it out. So we have tools that deploy designs onto these FPGA chips. And then we have a separate set of tools for simulating hardware. And like I said, they're both tricky to use. So you should feel free to help other students with software problems. But obviously you can't collaborate on designs or share designs, that kind of stuff. Okay. So just keep that in mind. Section 14 is the attendance policy. As I mentioned, you have to be in lab, to use the FPGA boards. You can't take those out. But if you miss a lecture, it's fine. You can always watch it online. Section 15 says that we're working in groups of 2. If you want to work alone, you're more than welcome to, assuming we have enough stations in the lab to accommodate groups of 1. But if you're in a group of 1, you're still going to be held to the same standards and expectations as a group of 2, right? Let's see, Section 16 says your projects must compile in both hardware and software to receive any partial credit. Only one member of each team or group needs to submit the project online, and both will get the same grade. We're going to be doing project demos, generally with the TAs. So both team members should be present at the demos because the TA will ask you questions about your design as you demonstrate it. And we have a due date time of 11:59 on the due date to receive full credit, but there's a fairly lax late policy. We only charge you a 5% grade penalty per school day that you're late on a project, and it's capped at 30%. So, and the reason for this is because, as I mentioned, the projects build on one another. So if you're running late on one project, you're going to start running late on the following project. So you could, in theory, turn in everything like the last week of class, and you only would get a 30% late penalty on those, right? At most. Right? Does it make sense? The cutoff date, though, for submitting is December 6th, which is a Friday. So make sure you get everything turned in by then. And you can only submit one version of any project, which I learned the hard way to create that rule. Okay, any questions about the syllabus? Yes?
You mentioned here that there will probably require extra time in
Yes.
the lab. Is that something that we have to schedule? To be?
No. The lab is, there's one other course taught in the lab, and I'll post the times for that. It's a Tuesday, Thursday. I think it's 10 a.m. to noon on Tuesday, Thursday. So that's the only time you can't go in, but any other time you can go in. Oh, and the lab combination is on the first page under section 2. There's a combination lock. It's 45213. So you can go in there, I guess, anytime, right? Because I think your Carolina card gets you into the building after hours, right? So, yeah. So generally, you're most likely going to have to spend more time working in the lab than we have scheduled in our lab sections, right? Because we only have 75 minutes per week scheduled, right? Makes sense? Okay, so let me first switch over here to Moodle just to show you what that looks like. So this is the Moodle site, and you'll see that I've got a link to the lecture recordings, and all the downloadable materials are on there. And I've got study guides and reference guides, and we have some stuff that we have a virtual machine image that you can set up if you want to use the tools at home. If you need any help setting that up, let me know. And then I have a schedule on here, and each week I'll have a row in this table where you can access the lecture slides, the lecture video, and then if there's a quiz or an exam, you can click through on there. The exams will be on Moodle too, by the way. So you can take them online. Okay, I think I covered everything there. Let's switch back over here to a lecture. So the objective of this class, there's two objectives. The first is to, as a continuation of what you learned in 211. Y'all remember 211? Digital logic design? So we're going to teach you how to apply the concepts you learned in digital logic design in a way where you can apply them in a practical, larger scale way, right? So we're going to, using CAD tools and a hardware description language called System Verilog. And the second objective is for you to actually build a CPU from scratch and have it do something practical. So, you can say that you built a computer from scratch, right? A CPU. And that'll be the CPU that you learned about in 212. So in a way, this is a direct continuation of both 211 and 212. You're going to be using the digital logic you learned in 211 to build the CPU that you studied in 212, right? That's in a nutshell what this class is about. And so in 211, what you should have done in there, and I realize that it's been 2 years maybe since you've taken 211, but hopefully you remember that in that class you designed or you wrote Boolean logic equations, and the idea was that that's a mathematical representation of a behavior of a digital logic circuit, right? So that's a behavioral description of what a circuit is doing functionally. And then you can take that behavior and you could deploy it, or you could implement it as a digital logic circuit, which I think you guys probably just did with a pencil and paper, right? You just kind of drew it, or you might use Logic Sim, which is a real simple CAD tool where you can draw circuits and wire, gates, logic gates and wires, right? And then, you can take that digital logic and you can minimize it. You can convert it into an equivalent, a functionally equivalent but simpler form with less gates or less wires or less fan-in, using like Karnaugh maps, for instance, or a Quine-McCluskey method. And then you could, implement that equivalent circuit. And then hopefully you got some practice with breadboards, plugging the chips in the breadboards and the wires, and actually building the circuits that way. And that would be the physical implementation. So you've got what they typically call the Boolean logic is the behavioral description of a circuit. The gates, the circuit design with the gates, that's the structural representation. And then this would be the physical implementation where you actually pick out chips and put them down, and you take every one of these logic gates and you allocate a physical gate on a chip corresponding to each of these logical gates in the circuit, right? So hopefully you were able to do that. I know nowadays they're using Arduinos and stuff in there now. They're not doing as much of this low-level stuff as they used to. But you probably, or you might have thought at the time that how would you build a real chip with this? Because a few years ago I estimated that a modern CPU could be built with breadboards, but it would take 8 million of them. With those 7400 series chips. And then even if you were able to build one, it would be like 1,000 miles long. And then it would be impossible to debug it or reuse any parts of it to come out with the next version of the chip, because it would just be this massive rat's nest of wires, right? So obviously the way that you implemented the circuits wasn't very practical for large scale circuits, but you did learn the concepts behind digital logic, which is good. So how are we going to do it in this class? Well, instead of the breadboards, we're going to use these FPGA boards instead. An FPGA is essentially another form of a breadboard, basically. But instead of having to plop chips down into it and connect wires, it's a chip that can be electronically programmed to behave as any arbitrary digital logic circuit. So you basically, it's like having a breadboard in 7400 series chips that is electronically put together like by a robot, except it happens inside the chip on that board. That's basically what an FPGA is. It stands for Field Programmable Gate Array. It's a programmable logic chip. So we're going to replace the breadboards with an FPGA, and then instead of animation script there, instead of specifying the logic behavior as Boolean logic equations, instead we're going to replace that with a language called an HDL, a hardware description language. Sometimes it's called an RTL, a register transfer language. And there's two very popular versions, two popular HDLs. One's called Verilog, and the other one's called VHDL. And then there's some smaller ones too. The one we'll be using is Verilog. We used to use VHDL, but over time, Verilog seemed to started to gain more traction, especially in industry. And we're hoping to prepare you for hardware design jobs in industry. So we switched from VHDL to Verilog. But once you learn one, it's pretty easy to learn the other. In fact, in the textbook, every example in the textbook, they have both. It's kind of cool. Every single time they have a code snippet, they put the VHDL on the left and the Verilog on the right. So you can actually see how they correspond. And they're usually about the same length. Okay, so as I mentioned, an FPGA is a chip that when you apply power to it, it's a paperweight. It's completely useless. Until you program it, you send a bit stream in, 1 bit at a time, which takes a while. Takes like a minute to send all the bits in, because there's millions of bits you got to send in. But you send the bits in, and it configures the chip to... You're giving birth to a circuit when you do that. You've got a circuit that you design, and that circuit snaps into existence once you program the FPGA. And the way that works is the FPGA is it's a two-dimensional grid of lookup tables, each of which can be initialized in a way where they can become an arbitrary logic gate. And those lookup tables on this FPGA, I think, have 6 inputs and 1 output. So you end up with this FPGA has 115,000 6-input lookup tables that each can be a gate. So essentially there's 115,000 gates. That's the capacity of the chip. And then in between those gates, you have wires that are all connected through switch boxes, right? So you can configure those switch boxes like an old-timey telephone operator, that she'd put the wires in to establish connections. It's basically what happens. You can create arbitrary connections between those gates. So you could take the output of a gate and connect it to one or more inputs of another gate, right, inside that array. That's basically how it works. And then the FPGA also has flip-flops in there as well, in addition to the LUTs. And then they have DSP blocks, which are hardware multipliers, and reprogrammable I/O pads. You might say, how can you reprogram an I/O pad? You can have them work at different voltages. Like you can have an I/O pin that can be 3 volts or 2.5 volts, or it can be LVDS, low voltage differential signaling, where you use a pair of pins, alternate, to alternate their relative voltage. So they have all these things in there. And it's all programmable, right? In fact, that's the kind of the company motto of Xilinx, all programmable. These FPGAs are pretty big. They're the embedded version. They have classes of FPGAs that are for embedded systems, like that are used for low power applications. And then they have a class that are for server applications, like those are the real big ones that are for data centers. This one is an embedded one, but for an embedded FPGA, it's a big one. It's 115,000 gates is a giant embedded. It's almost a server level FPGA. It's kind of right on the boundary there. It's a little old though, and I just I just heard last week they're discontinuing this board, so we're going to have to switch to another one. But I still like this one better than anything that's out there now because it has, you'll notice that it's got a bunch of these switches and buttons and LEDs. It's actually, if you look at that board, it's amazing how much stuff they packed on there. And I think all that stuff was hand soldered for the most part. I mean, so it's incredible the amount of labor it took to put all that stuff on there. Because normally when you look at a circuit board, they kind of try to minimize the number of components on there to minimize the cost. But in this case, they've got, you know, sound and video and GPIO and different types of memories, and there's all kinds of stuff on there because it's intended to be an educational board, so you can pick and choose which components you want to use, right? And you might have used the same board in 313. We use the same board in 313 and 491 too, and we did that intentionally so you can get comfortable with it because, as I mentioned, that you know the tools are pretty awful, no matter which CAD company you go with. Okay, so as I mentioned, we're going to basically take the CPU design from 212, which was the MIPS CPU, and hopefully, and again, I know it's been maybe 2 years since you took 212 or a year, and I'll review. But hopefully you remember how that CPU was organized, right? There was an ALU in there and a register file and a control unit and instruction memory and data memory. And we're going to take that and basically translate it to HDL so we can deploy it on this FPGA. So you're not going to be necessarily designing the CPU, you're going to be implementing it. It's kind of a pre-made design. Of course, you have some flexibility on how you choose to implement it, right? But in general, we're going to be giving you like the hints about the design, and then the idea is to take that design and convert it to a text file, essentially. You know, you'll notice that design's not, that's a block diagram, right? That's a schematic. But when you do HDL design, you have to convert a schematic into code, right, into a text file. Now, in the past, we used to use a schematic capture tool in this class. It was called FPGA Advantage by this company, Mentor Graphics, which is now owned by Siemens or Microchip, or one of those companies bought it. But the idea is that you would draw the schematic and then it would generate the HDL for you. But we found that was more trouble than it was worth because, one, no companies actually design them that way. All the professionals use straight up HDL. They just type it into a text editor. That's what we discovered as we collaborated with companies. But also, if you use a schematic capture tool that generates the HDL and you get an error, it's going to point to a line in the code when you don't know what that corresponds to in the graphics, right? So we found through experience that it's better to just learn the HDL language, and so you're going to be writing code that implements a schematic, essentially, or Boolean logic, right? Which may seem counterintuitive at first, but that's the way it's done. So here's an example. So this is, if you look in here, I took the control unit, which is this block right here, and I converted it to Verilog. And you can see that basically you're instantiating something that kind of looks like an object, right, in an object-oriented language. But then you've got these pairs of connections. So you've got a port that's coming out of the block on the left, and then on the right in parentheses is the wire in the design that you've instantiated in. So basically what's happening here is that you're connecting ports to wires, right? Each one of these lines of code is just connecting one of the inputs or outputs of the control unit to a wire that's in that design, right? And so we call that structural HDL. Structural HDL is when you're basically just creating a block diagram in HDL. And then down here, this is a MUX. This is a multiplexer. And you probably remember multiplexers from 211. And you can see this is being implemented with a ternary assignment statement, right? And so this is behavioral HDL, because this is more of a direct implementation of logic, whereas this is just taking advantage of you've got a pre-made block, the control unit, and you're just putting it down and connecting it, right? So this is the structural and this is behavioral, and you can mix those in the same design. When you look at code though on the internet or that other people are designing, most of it's structural because the behavioral stuff is at the lowest levels, the leaves of the design, right? When you get down to the actual Boolean logic. Everything above there in abstraction is usually just structural, blocks that are instantiated and connected. I'll talk more about that in a minute. So one question I used to get a lot is why learn hardware design? So aside from the fact that you guys are mostly computer engineers, if not all of you, and you're probably interested in how CPUs work under the hood, right? And the fact that if you get a job as a hardware engineer, that's more of a specialized job, so it pays more, obviously. But outside of that, why would you learn hardware design? One of the reasons is another reason is that software isn't getting faster anymore, right? Just writing software. So back in the old days, they had Moore's law, which according to this result, which this came out of this is a really nice plot. What this is doing is it's comparing the performance, the benchmark performance of a bunch of machines against a baseline where the baseline is a VAX11. The VAX11 was probably the first widely, the first 32-bit processor, basically. It was the VAX11. And it came out in 1978. They announced it in 76, and I think you couldn't buy it until 78. And so they've normalized all these performances to that. And this is not peak performance. These are benchmark performance. This is actual performance observed by running a benchmark. So you can see, for instance, that like the IBM Power 4 at 1.3 gigahertz was 3,000 times faster than that VAX11 chip, right? And when you look at this chart, and it's plotted versus the year, you can see that from 1978 to 1986, there was a 25% improvement per year. And that means that the performance was doubling. At that rate, it would double every 3.1 years. And then from 1986 to 2003, the CPUs started to get faster, when every new CPU came out. And so you were getting on average a 52% improvement per year, which means the performance would double every 1.7 years, which is actually very close to what Moore's law predicted, which is 1.5 years. It's supposed to double every 18 months, right? But then things slowed down from 2003 to 2011. It was the doubling rate was 3.3 years. And then 2011 to 2015, it was doubling every 6.1 years. And now it's basically flat since 2015. So processors and thus software, the performance is doubling, in 20 years it would take to double your performance of your software. And of course, things continue to slow down. And so basically what that means is that if you want to introduce any new capability that's in any way tied to performance, then you can't just wait till the next CPU comes out. You're going to have to design some kind of specialized hardware, right? And so, like when I say new capabilities, what I'm talking about is, when you get things like self-driving cars and 4K video, in some respect, those capabilities come about from new algorithms and numerical methods and signal processing algorithms. But a lot of it is also because of the performance. The performance to do self-driving cars really, it wasn't really available until 2014. When you got, for example, animojis and computational photography and now this augmented reality stuff, most of that stuff is tied to computer vision and image processing and machine learning, artificial intelligence. And all that stuff all of these examples have real-time performance constraints. And so if you can't make those real-time performance constraints, then you don't get the capability, right? And all of those things came out of not just software, but those all require specialized hardware for all that stuff. They all are driven by coprocessors or accelerators or domain-specific architectures or whatever you want to call them. And you can see that, for example, if you look at a dye photograph of an embedded processor like Apple's chip, these are actually very hard to come by because Apple does not release these like Intel does. So these images actually came from people that destroy the chip and take a picture of it. And then they try to identify what's on the chip. And so if you look on there, the little area that I've shaded as white, that's the CPU. That's the CPU cores that run the software. Everything else around that is all specialized circuits for specific things, like graphics processors and AI processors and image processing and crypto and all that other stuff, and modems and interfaces and memory controllers and all that stuff. So you can see that if you just look at the real estate and how it's allocated, only about 12% of a chip is actually just CPUs, general purpose CPUs running the operating system, running software. The rest of it's all dedicated circuitry. So you've got hardware engineers doing all that. And the same thing is true also with CPUs, desktop CPUs, server CPUs. So Intel actually take pictures of their chips and just put it out there, which is kind of cool. They release all their die images and they annotate them too. And so you can see here, this is the Westmere from 2010. You can see that 72% of that chip was CPUs. And then as we go to the Ivy Bridge in 2013, only 47% of that chip was CPUs. And then the Broadwell from 2015, 20% of the CPUs. You can see that over half the chip now is processors, right? And so the idea is that there's no reason to allocate more space to processor cores because you just don't get anything back from that. There's no point in that. And it's better to allocate those transistors to processor graphics. Now, can you program the processor on the Intel CPU? Maybe, but it's really designed specifically for graphics and stuff like that, to unlock graphical capabilities. So as I mentioned, we're going to be using this FPGA board. It's called the DE2-115. It's got a what used to be owned by Altera, but then Intel bought the company Altera. So this is technically an Intel FPGA. And it's called a Cyclone 4. It's got 115,000 gates. Really cool board. It's like I said, it's a little old, but I got a soft spot for it just because it's just such a cool board. There's so much stuff on it. It's got the plexiglass top on it and stuff. So in the first 2/3 of the class, I am going to essentially teach this as a skills course, teaching you a language, right? Which it's kind of distasteful because it kind of comes off as kind of a vocational type of class where we're teaching you how to write a language. But the purpose of that is to try to get through that material as fast as we can so you can have the experience of designing and testing a CPU from scratch on this board. In the last third of the course, we'll switch gears a little bit and talk about more conceptual stuff. Specifically, we'll cover sequential logic, which you should have covered in 211, but they don't. And digital building blocks, like how to build multipliers and stuff like that, and multipliers and dividers, circuits. And then we'll talk about timing analysis, and then I'll get into CMOS logic, which is I used to teach a VLSI design course, which I don't teach anymore, but I took a piece of that class and I added it to the end of this class. So you can get an idea of what it's like to design an ASIC, an application-specific integrated circuit. That's if you don't want to use an FPGA, you want to just design an actual chip, a specialized chip, right? Now you might say, wait a minute, if you can deploy any digital logic on an FPGA, then why would anybody build a custom chip? The FPGA is about 10 times slower in terms of its clock rate than an ASIC, and it has about 10 times less density in terms of number of gates per area, right? So if you want a really high performance chip, you have to design an ASIC, which is why, for example, back in the day, there were like Bitcoin miners that were deployed on FPGAs, and FPGA is a pretty good platform for Bitcoin mining, except if you design an ASIC, a specialized chip, it's like 10 times faster. So now, if you want to get the best, fastest Bitcoin mining, you got to buy a specialized chip for that, right? But the design process is very similar. So ASICs are also designed with HDL, right? The only difference is in the tools. With an FPGA, you take the HDL code and you basically compile it down into a bit stream for the FPGA, whereas with an ASIC, you compile it down into mask shapes, polygons that you send off to a fab over in Taiwan, and they'll use their piranha acid and sulfuric acid and horrible, deadly, nasty chemicals to make it, right? That no American wants to be involved with, right? That stuff. And then send it back, right? But that's really expensive and you got to wait a long time for it to come back. And the first one will never work. So you get the one back and it's never going to work. And then you got to fix it and try again. Do Rev 2. Okay, so let's see. So let's talk a little bit about assembly language, which might seem off topic here because I just got done talking about hardware. But the problem is that in order to build a CPU, you have to understand instruction set architecture. And you should have covered that in 212, but I've learned through experience that a lot of you start to forget that because that's pretty much the only time in the curriculum you use assembly language is in 212. Now, people have argued that we shouldn't even cover it in 212 because no one programs in assembly language, right, in industry. No one uses assembly language because compilers are really good. And that's true. You know, compilers will convert your C++ to assembly for you, right? And that's true. Yeah, you probably will never write assembly code in your jobs. Very, very, very unlikely. However, if you want to design a CPU or know how a CPU works, you have to understand the assembly language because that is the native language of the hardware. So the whole purpose of a CPU is to fetch and execute instructions. And if you don't understand what those instructions do or how they're made up, then you can't design the CPU, right? So we're teaching assembly not because we think you're going to get a job hammering out, thousands of lines of assembly, but because you have to know it to design the CPU. So you have this architecture or instruction set architecture, which defines everything you need to know to program a CPU. And this is the information that's publicly available. So Intel, for instance, they're very good. In fact, I always thought one of the reasons Intel was as successful as they were historically, and I think they may die at some point as they're losing, their market share sort of is shrinking. But the reason why Intel was very successful was one, they had a general purpose processor. It was pretty good at doing just about everything. But also, they were very aggressive about getting their instruction set architecture out there, right? Because they wanted people to know about it. For years, if you went to Intel's website, you could just request it, and they would send you a 3-volume set for free. Printed books, like physical books. They would send them to you at night. And I always thought that was cool. They eventually just recently stopped doing that, but you can still get the PDF copies of it. They very famously have a 3-volume set, and it's everything you need to know about the Intel processor to use it. Now, what they don't tell you, though, is how the processor actually executes those instructions, what happens under the hood, right, or how it works internally. That's a jealously guarded secret. So, for example, no one knows how Intel's cache works, for instance, because it's a secret, right? And so, but everyone knows how to program the chip. They just don't know how it works underneath. So underneath is the microarchitecture, right? So the architecture is kind of like, how to drive a car, right? And then the microarchitecture is how the engine works, basically. Essentially is what this is all about. But in order to build the microarchitecture, you have to understand the architecture. So, so let's see, I mentioned, it's everything you need to know. It's the instructions, it's the machine, the way that you translate the instructions in the binary, the machine code. It's this, how the page tables are set up and how you set up the system calls so you can build an operating system. Everything you need to know, that's all in the instruction set architecture. And the microarchitecture is the internal engines of how those instructions are executed. And so you guys, of course, you've learned high-level languages in the curriculum. You should, at this point, know C++ if you've taken 240. C++ program basically has one line of code for every 10 instructions, right? So every line of code in C++ is going to be translated into about 10 instructions that the CPU will execute. If you like Java, Java is not translated directly, although it can if you do a just-in-time compile. But generally speaking, Java is a bytecode interpreted language. It's an interpreted language, but it's interpreting a binary language. And so one line of Java code might require 10 to 100 instructions executed on the CPU. And if you're writing Python, Python is purely interpreted. And so if you consider, the overheads of the interpreter, Python's going to require about 100 to 1,000 instructions executed per line of Python code at least. So, but basically the idea is all those high-level languages correspond to a set of instructions that are executed on the CPU. And so you probably remember that instructions have mnemonics. So these are primitive operations, and they're identified by mnemonic, which is a short English word, right? Sometimes it's easy to figure out, like add, and other times you'll see CSRRW, and you're like, what the hell is that? Like it's some kind of crazy acronym, right? So that's the mnemonics, and then in this day and age, you've got registers, which are programmable. Program-controlled memory on the CPU called registers, and the instructions operate on the registers, and then you perform load and store instructions to exchange values and registers with your RAM, with your external storage, right? So I mentioned we're going to use RISC-V. We switched to RISC-V from MIPS a few years ago in this class. They haven't done that yet in 2.12. They probably eventually will. They're very similar. The only difference is that RISC-V is, it's very similar to MIPS, but it's an open architecture. I think MIPS is now too, but historically MIPS was, you had to license it. And so technically it wasn't legal for us to be building MIPS processors in the university. But RISC-V is an open standard and it's new. And the thing I like about RISC-V is that it was the same people behind both. Right? It was the David Patterson at Berkeley. But they fixed a lot of the annoyances of MIPS had some annoying things to it, right? And they fixed those things in RISC-V. So they took all the stuff that they learned over the past 40 years and they used it to build RISC-V, which is, it's nicer. It's more thought out than MIPS was. So for example, here's some examples. So you might have remembered in MIPS that the destination register could be in different locations in the instruction. It could be an RD field or an RT field, and then you had to add hardware to be able to steer in whichever field you wanted to write to, what register you want to write to. That was ridiculous. But they fixed that in RISC-V. Now there's just only one register destination field. And the MIPS had this thing where by default, all shift instructions were constant shift amounts, but no one ever used them. And then they allocated 5 bits in the instruction for the shift amount, which was almost always 0. Just wasted bits. So they did that. MIPS had this thing where you sometimes use 0 extended immediates and sometimes you sign extended immediates, and you had to figure that out in the control unit. RISC-V just says, no, sign extend everything. And then MIPS had you could jump and link, or you could not jump and link, and it's like, well, what's the point? Just always jump and link. Why are we doing this, MIPS? And so RISC just always jumps and links, and if you don't want to link, then you just put register 0 in your link target and no problem. However, RISC-V has some of the annoyances that irritate me. Like for example, there's no index registers. So you can't just say, I want to have an address and add the contents of this register to the address. In other words, indexing operation, which every high-level language uses and relies on for arrays, not implemented. So you have to basically calculate addresses and add the offset manually, which is crap. There's no way to auto-increment address registers. A lot of other architectures have that, but this RISC-V doesn't. And then they have this weird thing where the destination is always on the left for everything, except for a store instruction where it's on the right, which is stupid. So they kept those things for some reason. Now, some of those things, though, those decisions were made deliberately, though, because if they provided an index register, they would have to have extra hardware in there in order to add. They would have to take the address and add the index, right? And they might even need another port on the register file to do that. And so those things they did deliberately because they wanted to have the instructions as simple as possible, because if you have an index register and a dedicated adder for that, you're only going to use it in about 10% of all instructions, and the other 90% of the time it's going to be idle hardware. So that's part of the reason they did it for efficiency reasons. So some of those decisions were deliberate. And then RISC-V has some additional complexity, though, over MIPS, where the instruction encoding is a lot wackier. So remember in MIPS, there was basically just 3 instruction types, so R type, I type, and J type, right? Now there's like a gazillion in RISC-V, and they're all crazy. They've got, in order to figure it out, you have to take bits from this part of the instruction and bits from this part of the instruction and mash them together and reorder them in a different way, and it's awful. But again, they did that for, to simplify the hardware, and they assumed that it wouldn't really affect many people because most people don't worry about how the assembly instruction is translated to machine code, right? Because the assembler does that. However, if you're in this class and you're building an actual processor, now you have to care about that because you're going to have to design the hardware that interprets those instructions. So when we get to that part in the class, you're going to look at these U-type instruction and B-type instruction. You're going to be like, how, this is terrible. In fact, it's so confusing that I have to just give you the code for it because it's just so arbitrary the way they shuffle. MIPS tried to make it simple in the encoding format, but RISC just threw that away. But aside from that, everything is pretty simple. So as I mentioned, RISC-V is named after the reduced instruction set computer. That's what RISC stands for. And basically the idea is that you want to make each instruction as simple as possible, so you can achieve a very high rate of instruction execution. The problem with that is that when you make them simple, it is murderous to write code in that instruction language, that assembly language, because the instructions only do a little tiny bit of work, and so you have to write a whole lot of instruction to do anything meaningful. But they assume that the compiler would normally do that, so it wouldn't hurt anybody, except, again, people in this class where we're going to be writing assembly code. So unfortunately, but I try to keep it to a minimum, right? But yeah, so, and I'll show you some examples of that in a minute. But the idea is that if you make the instructions simple, you can make them fast. So you can chew through them really fast. And since memory is cheap, we don't have to worry about memory. On the other hand, a CISC instruction set architecture allows you to do a lot of work per instruction. You can do a lot of, the instructions are more abstract in the sense they do more, they perform more workload. And you'd have to have less instructions to make a program, but then you end up with hardware that's you end up with specialized hardware that you don't use very much, right? Now you might say, wait a minute, I thought you said that there's specialized hardware now in every embedded processor like the Apple chip. They have whole regions of the chip that are specialized. Yeah, kind of weird, right? Also, RISC just finalized their vector extensions, which is kind of cool. I don't know, it may be too aggressive to try to do that in this class, but they have these vector instructions now. But vector instructions do a lot of work. They process vector operations with one instruction. And, only vector code will use those, right? And also, compilers aren't good enough to, well, sometimes you can, but generally speaking, to get efficient use out of vector instructions, you have to write an assembly code, right? Or use intrinsics, which are like little functions that call out specific assembly instructions. So I guess my point is that we're kind of going back to CISC a little bit in some ways, right? Where there is this push to go back towards the CISC philosophy. Okay, anyway, so RISC-V, just like MIPS, has 32 general purpose registers. You might think, geez, they never increased that? It's been, what, 40 years? No, still 32. That way, the advantage of that is that it only takes 5 bits to specify a register address, so you can fit that into an instruction better. You might remember in MIPS, when you wrote MIPS code, hopefully you guys wrote MIPS code in 212, the registers were, you put a $ in a number from 0 to 31, or you could use the special symbolic links like $A1 or $S0. In RISC, it's X instead of $. So X0 to X31. Why? I don't know. Don't know why they changed that. They both have a special register 0, which always has the value of 0 in it. That can't be overridden. There is a reason for that. A lot of times you can use that to, like, for example, add something to 0, right? Sometimes you want to do that if you want to initialize a register. Or, as I mentioned earlier, in RISC-V, every jump instruction is a jump and link. It records the return address, and sometimes you just want to put 0 in there for the return address, right? So you can write to register 0 if you just don't want to write something, right? put register 0, because you're allowed to write to it. It just doesn't retain the value you wrote to it. Because when you read, it's always 0. And then, of course, you also have immediates too. So some instructions, usually the mnemonic ends in I. That's when you just can add a number in there instead of a register as the second operand. Okay, so I have a few slides here where I'm just going to briefly, hopefully you guys know this, right? You guys know this stuff? You guys remember assembly language? I just want to go through a few kind of examples and some things that I think are really the part of writing code in assembly that's hard, right? There's a few things that make it hard. So for example, one of the things is that as a programmer, you can only do operations on registers, but you have to allocate those registers by hand. So you have to decide which registers you want to use, what they're being used for, and when to recycle them and use them for something else. In other words, certain registers are tied to certain variables for a certain amount of time, and then they get used for other variables, right? It's not a single assignment system. It's a, the registers are a shared resource, and they have to be used and reused for other things, right? And that's a problem because it's really hard to remember what register is what when you're writing code. It's tough. It's meant to be done by software. It's meant to be done by a compiler. It's not really something a human can do very well. And there's no good way to do it. I mean, you can put comments in your code and say, register 12 is my I variable, right? That's about the best you can do. But even then, it's hard to keep track of that, right? And sometimes you'll recycle a register too early and you blow away a value that you wanted to keep and that kind of stuff. So here's an example. So if you have a line of C code that says f equals g plus h minus I plus I, minus I plus j rather, computers can only add, subtract, multiply, or divide 2 values at a time. And so if you want to do something with more than 2 values, you have to break it down into sub-expressions. So in this case, you want to add g and h, and you want to add I and j, and then subtract those 2 intermediate values, right? The problem is that you can't do it directly, right? Because you have to first load those 4 variables into registers before you can actually, number crunch on them. And then you have to, the result has to be stored back. So you have to have, in this case, you have to load the 4 values, and then here's where you're associating variable names with registers. Now, as I mentioned, the registers are numbered from 0 to 31, but they also have these special names like S1 through S4. And you can decide if you want to use the special names. Those special names are listed for you in the software we're going to use to simulate this. It's called RARS, similar to Mars that you might have used in 212. Or I guess Punyan uses another one now. There's multiple simulators. But there's just alternative names for these guys. So I loaded G through J in registers S1 through S4, and then I did my add instructions. But in addition to having to associate these 4 variables with 4 registers, I also had to come up with 2 additional registers here to serve as the temporary values that stored the intermediate sums of the two sub-expressions, right? Which I used T0 and T1, right? And then so you have to keep track of all this. So there's actually 6 registers associated with the variables I loaded. There's 2 temporaries, and there's the 1 F that I have to store back, right? So that can get complicated fast, but that's just a skill that you just have to develop, keeping track of those registers. So here's another example. It's very similar. It's just another mathematical expression that had to be broken down. Now, by the way, you don't have to always do it in that order. For example, you see that I did my 4 loads first, and then I did my arithmetic. You could have just loaded, you could change the order here a little bit and load G and H and then add those and then load I and J, and then you can recycle that. Actually, I don't think you can. No, you can't recycle the temporary because you got to have 2 registers to hold those 2 temporary values, right? So, yeah, there's answers will vary there, but the point is that you have to keep track of all the registers. But probably the worst thing about assembly, and this is what really irritates me. So in a high-level language, you have an if construct, right? Where you say if condition, then and you have code, right? So the code that's immediately underneath the if is what gets executed if the if condition was true, right? And then you have an else clause, and the else is what happens if the condition was false. So anyone that's been programming has been conditioned to always have in an if statement the true clause first, the else clause second. The problem is that generally you can't do that in assembly unless you write really inefficient, unless you add extra instructions, right? What ends up having to happen in assembly code is you kind of have to reverse it, right? You're going to have you do a conditional, in this case, branch, because the decisions are handled by branches is the problem. So what you want to do is test the condition, and if that condition is true, you jump down to somewhere else in the code. And if it's false, you go to what's called the fall through, which is underneath the branch, right? Make sense? Right? So if the condition is false, you do the fall through. But the problem is, in a high-level language program, the fall through is the true part, right? In other words, you don't want to go somewhere else if the condition is true. You want to continue, you just want to go straight. You want to go underneath the if statement, right? So what ends up happening is in assembly language, usually you have to complement the condition, right? You say, if you want to know if A is less than B, you say, well, what if A is greater than or equal to B, then jump to the else part. And then your fall through is the true part, right? Does it make sense? Right? So in other words, you have to reverse all your if statements, right? Now, you could do something where you could test to see if it's true, and then you could jump to another thing. You could make it more complicated and have the true clause be higher, but it's going to take more instructions. And generally what you do is when you're translating high-level code to assembly, you just have to reverse the condition of your ifs. Yeah, so, all right. Another issue here is arrays. Arrays are a real pain because, as I mentioned earlier, there's no way to index load and store instructions at least not in MIPS and not in ARM and not in RISC-V. You can do this on the Texas Instruments DSP architecture. They have index registers. IBM mainframe has index registers. So there's other ones that have this, but these puritanical RISC architectures don't have index registers. So there's no way to put an index. So you have to calculate all of your effective addresses, right, manually, meaning effective address is the base address where the array starts, and then you have to take the index and multiply that index by the element size and then add it to the base address and then use that to do your load and stores, and you have to do that for every time you access the array, right? Also, when you're doing that indexing, as I mentioned, you have to multiply the index by the element size. So if you have an array of 32-bit numbers, you have to constantly multiply the index by 4, right? Or you could just add 4 as you walk through the array, but then the problem is, what about your loop control variable, this I, right? So I've got a loop here that goes from I equals 0, I less than 100, I plus plus. I'm only adding 1 to my loop control variable, but yet when I use my effective address calculation, I have to do it in units of 4, right? Because the array is elements of 4 bytes each, right? And that all has to be done manually. There's no way around that. You just have to figure that out. So that's another thing about assembly that's a pain. And that's what I mentioned here. Yeah, so in this case, this one is even more egregious because, you know, I've got two separate arrays that I'm reading one array, I'm writing one array, right? And I have to keep track of that I variable, you know, that walks through it to figure out how many iterations I want to take. And all of that has to be maintained separately. And then the other thing, too, that always irritates students in this class is that you can't compare anything to a constant in one instruction. So you just can't say if register 5 is less than 10, no. You can only compare two registers. So meaning that you have to load you have to preload, pre-chamber the thing you want to compare against, and that's really irritating because a lot of for loops have constant bounds, right? But no, you got to do multiple instructions for that. Okay, so so that was my really quick review of assembly code. So in our first lab, just to get everyone up to speed with RISC-V and to refresh your assembly language knowledge, our first lab is going to just be a assembly language lab. It's a simple one though, and we're going to reuse it as a benchmark, as a test case for our CPU. So the first lab is a numerical method for calculating the square root of a number, right? So you put in a number in, you calculate the square root. And so it's a fairly short program, and then we'll write that in lab 1, and then we're going to use that when we build the CPU to be able to have it run that, and we'll implement a calculator, on the FPGA board, right? So it's not like you're not writing it for nothing. You get to reuse it later. And the nice thing is that because you wrote the code, you understand what it's supposed to be doing. It's easier to debug it when you know what's supposed to be happening as your processor executes the code, as opposed to me just giving you a test program and you not knowing what that test program is supposed to be doing. It's harder to test the CPU. Also, the other reason we're doing this is we learned through experience that if you assign the CPU lab and you have the class write the code to test on it, that's a recipe for disaster, because if you're simultaneously designing the hardware and the software, and then you put them together and it doesn't work, you don't know what the problem is. You don't know if it's a hardware problem or a software problem. So this way, if you write the software, the test program first is a separate lab, and then you get it graded, you know if it works. Then when you test your hardware, you know that the software is bulletproof. So if it doesn't work, it's got to be the hardware, right? So that's the thinking here with this first lab. But I'm not just trying to torture you with writing RISC assembly, which is torturous. So we've got let's see, we've got 6 different instructions really that you'll use. There's what I call the arithmetic logical shift comparison instructions that are register based. So they have two operand registers and 1 destination register. The destination comes first. You might say, doesn't it always? No, sometimes it doesn't. TI's comes last, IBM's comes last. It depends on the architecture. The convention is for the destination to be listed first, unless it's a store instruction, and then they switch it for some reason. I don't understand. All right, so like if you say add x1, x2, x3, it adds the contents of registers x2 and x3 and puts the result into register x1. Then you have the versions of those instructions that have an immediate, right? That's basically a constant. You have to have special hardware support for that though, right? So it's not free. You have to implement those I-type instructions, immediate instructions. In RISC-V, the immediates are only 12 bits. You might remember there were 16 bits in MIPS, right? They have a U-type too that has a bigger immediate, but a lot of these immediate instructions only have a 12-bit immediate. They've shrunk it down a little bit because RISC-V guys thought, well, usually when you have an immediate instruction, it's usually a small number. So you shouldn't need any number outside the range. And it's also sign extended too, which means the immediates are all signed, right? Which means you can only put a value from -2048 to +2047 in an immediate. You can put bigger numbers, but then you have to break it out into multiple instructions, right? To do that. It becomes a pseudo instruction, not a one-to-one machine, assembly to machine instruction. Okay, then you've got the branches. Branches compare 2 registers and either take the branch or not. Take the branch, it goes to a label, so it just jumps somewhere else in your code. It could be down or up, right? Then there's jumps. As I mentioned, all the jump instructions, they're unconditional, but they're all linking jumps. So they link back. So this has implications for you guys because that means a jump instruction will always write a register. So you have to deal with the write back for the jumps, right? Which is something that you didn't have with, always have with MIPS. Load and store instructions. I'll talk a little bit more about this. Loads and stores are a little strange because in assembly language, when you do a load or store, you just put a label there usually, a symbol, because the assembler has a symbol table. The assembler keeps track of a symbol table. So it creates a table that maps the variables to addresses. And then it'll substitute in instructions to create those addresses for you, right, in the machine code. But that's not very useful if you're designing the hardware, because the way that it's run in the hardware is In the hardware, you just give it a base register, like a pointer. You guys know about pointers, right? Like in C, pointers. So a pointer is an integer, unsigned integer, that's a memory address. And to use the pointer, you have to dereference it, meaning that you take that address and you go to the corresponding location in memory, which then you can read or write. That's called a dereferencing operation. So the way the hardware instructions work is through a dereferencing operation. You give it a pointer, which is what they call the base register, and you can put a fixed offset on there if you want, but it's fixed. It's not an index. It's got to be fixed at compile time. So basically, it's just a pointer with a constant offset that is dereferenced when you load or store. That's what hardware does. In the assembler, if you use a symbol in there, the assembler has a symbol table where it takes the symbol's address and it converts it into instructions that build that base address for you, that base register, that sets the base register with immediate instructions, right? So you guys, when you write your code for Lab 1, you can use symbolic loads and stores, but you have to be aware of the fact that those are going to be translated to machine instructions. So the machine instructions are what you're actually going to be implementing in your hardware, right? Okay, and then you've got coprocessor instructions. So we need a way to do I/O. We have to do hardware-software interfacing in this class. Very limited, but we need a way to bring inputs from the switches on the FPGA board into the CPU, and we need a way to get data from the CPU out to the hex displays, which are those 7-segment displays on the board. How do you do that? Well, in real CPUs, the way you do that is through what's called memory mapped I/O, which is you do it through load and store instructions. But in this class, we're going to take advantage of a feature in RISC-V called a coprocessor read-write instruction, CSRRW instruction. And that instruction allows you to just basically go direct I/O from a register. And so we're going to use that to interface, to do human interfacing to your CPU. Make sense? And that way we can avoid having to do loads and stores altogether in the actual hardware. But you can still use them when you're simulating, obviously. Okay, here's an example of that. So, and this is a little weird too, by the way. Notice I have this var declared in the data segment of my code, and then I can say load word var. Right? Now var is at a specific address. The assembler knows what address that's at because it's basically the beginning of the data segment and knows where the data segment is. And so that one instruction is going to be translated to an AUIPC instruction, which when I first saw that, I was like, what is that? That's different. What is that? That is an instruction that actually takes the program counter and adds an immediate to it, which makes no sense because the program counter is going to be in the text segment. The program counter is pointing to your code. So why would I use the program counter to address data? They're in two different places, radically different addresses. I don't know why they do that. That's weird. Makes no sense to me. Now in MIPS, the way it worked was they just used a load immediate. They just put a hard-coded address. They didn't try to make it relative to the program counter like RISC-V. So that's weird. That might just be a thing that RARS does. I don't know if maybe actual RISC-V assemblers don't do that. I don't know, but it does. That's weird. But we're not going to implement that instruction, so we'll have to avoid using anything that generates that instruction. We're not implementing the whole instruction set. I should have mentioned that. We're only going to do a part of the instruction set, so we have to restrict our code to only the instructions that we implement, right? So we're going to implement the most common ones, and the more esoteric ones like that we won't worry about. Okay? We're not trying to build a complete RISC-V architecture. Okay, any questions so far? Okay, I will talk more about this in, I'll talk more about this in lab this week. But I just want to give you a little introduction here while I have a few minutes left. So if you look at the slides here, I've got a bunch of example instructions for you. We also have some reference guides. So in the first lab, we're going to be doing the square root calculation. The problem with square root is that you pretty much have to have fractional numbers when you start doing square roots. Should have complex numbers too, for that matter, if you take a square root of a negative number. Right? But we won't do negative square. We won't do imaginary numbers. But we do need fractional numbers. So how do you do fractional numbers? Well, you guys were probably taught if you need fractional numbers, use floating point, right? Floating point numbers. But we're not going to do floating point because we just don't have enough time to implement floating point. That would be cool, though. I'd like to do floating point. But we're just going to do integer instructions. So how can you do fractional numbers if you only have integer instructions? You use something called fixed point. And this is something that I always have a really difficult time explaining this. I've never found a great way to explain this. Because the problem is that you guys are accustomed to data types having an inherent like sort of hardware implementation of data types, right? If you put a floating point number, there's hardware floating point. You know, if you put a string, you know, the strings are processed with like bytes, loads, and stores, right? And also the compiler takes care of strings for you. It takes care of floating point, right? It takes care of that for you. Fixed point is when you have an integer and you pretend like it's a fractional number by imagining in your brain that there is a scalar being applied to it. So in other words, you say this is an integer, but pretend like whatever number is stored in that integer register, it should be divided by 256 in reality. So if the value 1 is in that register, it's actually 1 over 256, right? And if the value 10 is in that register, it's actually really 10 over 256. You're not going to see it that way in the debugger. You're not going to see it that way in the simulator. But you pretend. You say, I'm going to just assume that there's a scaling factor being done. What you're really doing is you're just assuming that the decimal point, although technically it's a radix point because these are binary numbers, decimal point is for decimal numbers, base 10. But I always call it a decimal point because no one knows what a radix point is. But radix, basically, it's the point at which the whole bits stop and the fractional bits begin, right? So if I put my decimal point there, right there, then I have 6-bit number and 3 are whole bits and 3 are fractional bits, right? Well, what that really means is that I'm assuming that whatever's in that number is being scaled by 1 over 2 to the third power, or being multiplied by 2 to the negative third power. Right? In other words, that number is an integer, but it represents eighths, not wholes, not ones, right? That's really all that means, right? Make sense? Right? Now you could do it the other way too. You could put the decimal point over here off to the right, in which case the least significant bit may carry a significance of not 2 to the 0th power, but 2 to the 10th power, right? So every bit here could be at 1024, right? Or if I put the decimal point there, then the unit in the last place, or the least significant bit, will carry a significance of 2 to the negative third power, right? Which is 1/8, right? But you're just pretending, right? It's just being done by the programmer, right? But it still works. Mathematically, it still works out. All I have to do is just assign a different significance to the bits that are in a value, right? And you can still calculate fractional values this way, and you don't need the floating point hardware. The downside, you might say, well, if you can do that, why would anyone use floating point? What's the point of floating point? Well, floating point gives you a very big dynamic range because you can put the decimal point wherever you want, like at runtime. With fixed point, it's fixed. So what ends up happening is that the dynamic range of that number is going to be fixed between the highest and lowest number. And the other problem is that the precision. Remember that the precision is the number of significant digits you have, right? So any leading zeros don't count. So if you have a fixed point number that's 32 bits, you might say, oh, I have 32 bits of precision. No, you don't. The number of bits of precision depends on the number of leading zeros that are in that register. So if you have like a 32-bit number and you have 30 leading zeros, and there's only 2 bits of precision there, right? So So that's a downside of fixed point. But we can still use it to calculate like the square root value, and I'll talk more about that in lab, okay? And that'll be a first assignment. All right, see you on Wednesday or Friday, depending on what section you're in.
Thank you.
Thank you.